So Conrad has a really good point. A linked list is a very good way to kind of destroy cache locality, and that's accurate. It's in some sense, maybe lower than. Oh, is the music still going? Oh, it's not pumping through my. How about? Should we have some background music maybe there, or what do people think about the background music? Actually, I'll take it away. I might just remove it so we can chat. It's kind of annoying. People can listen to their own music. Apologies. I'm such an amateur at this. I feel as though so we're creating a binary package. I want to open it up, open a folder, and it's this one here. So I do trust the authors of this package. And in fact, so what we essentially want to do is have something which we can have a linked list is conceptually, we have some item, let's say a list over T, over some value type. And in fact, we'll make it super simple for ourselves. We'll say that we're over integers, and everyone uses i32 because this is a 4-byte integer. It's kind of relatively commonplace. I'll take Conrad's comment down as well, because although it is accurate, it's kind of funny. Keep the music. Oh no, we've got we've got a fight. I'm going to I think I will actually leave it off. So as conceptually, we have next, and we want some the next item in the list. In fact, we probably want like maybe something that feels like option of list i32, because we might be at the end. And this is actually okay. You could imagine, so this is this is how Lisp canonically works, except instead of so they have used a stupid word called cons, and that actually used to mean something in the 60s. Now a a doubly linked list really goes against Rust's borrow checker. And this is the problem, that essentially we've had a couple of requests to go back onto the music. So I will play. We'll do that. It makes it much difficult, like if I'm doing like post edits to remove it, but that's all good. Now okay, where are we at? Okay, so what we're doing is we're trying to implement something conceptually like this, so we could access the next item and the previous item. Now the problem is that Rust really likes to have a specific owner, and if we can have references in 2 directions, we actually encounter issues with the borrow checker, like big issues. The borrow checker gets very angry very, very fast. And this is a canonical example of a case whereby people try to implement these quote-unquote basic data structures in Rust and get very confused very, very quickly. And is there a problem because i32 is a copy? No. Oh, so this is this question. Is there a problem because i32? No, it doesn't matter at all in this case. We can actually just have some generic type T, and at this stage it's fine. This list here is sort of terrible. We can't really do much with it, but this is conceptually what we want. So I will leave that there just as like a thought experiment. So yeah, and people laugh at Rust because they're like, you can't implement. It's impossible to implement like these basic things in Rust, and in many cases it's accurate, because what they're saying is like in C++ or C we could just have pointers to places, and it's super easy. And I'm going to show you that we can get actually pretty close to what we mean by the way that the C++ would work in it. I look at things by creating a list that looks pretty close to what we just had, except instead of option list, we have star mut and or mute, and that is a mutable pointer to some other node. Now, what's interesting about this is that essentially it may be null. We may have a null pointer at the end of this, and that indicates that there's no actual node there. So conceptually, from a C programmer's way of looking at this, a raw pointer to some type is conceptually equivalent to option of a pointer, or some reference to T, right? Or in fact, in this case, it would be node T. Now, in Rust, we don't we are going to have to double check every time we try to dereference the pointer and access the node, that it is not null that we get back, because if it is, the program will crash. Now, do we have any? So partial inequality is not. Okay. So this partial equality thing is not actually necessary at this point. I'll actually leave it out. So here was the question: why was partial equality introduced? Isn't a linked list unordered? Now, the partial equality is there for later on when we go and search through the list. It will, when we want to go and find things in a list, or maybe remove a specific item, we're going to have some way of comparing against one item, one sort of needle, and find the needle in the haystack. And we'll require that any value, so any value T, implements partial equality, which means we can compare them against other values. And essentially it is the way that Rust has overloaded the double equal symbol, or the test for equality. What you're referring to in terms of ordering is actually a different trait called partial ord. And partial ord is partial ordering semantics, which isn't required as well. The reason why they're called partial relates most specifically to the floating point semantics, because there are some bit patterns which actually are not defined in terms of equality. The same bit pattern, actually, if you had two values of exactly the same, they're actually defined as like being an unequal. These are not a number type. So you have a question here: why can't we use node option? We can. I'm just being hard on myself and saying, well, like, if you really want to do raw pointers in Rust, you can. And so let's like make things hard on ourselves and do that. But again, the reason, sort of more broadly, why you can't have references in both directions, because there'll be ambiguous owners once we have multiple nodes. So you can't have references going in both directions all the way along the list. So that was this question here. Why can't we have node option T? Cool. Right. So now I need to go a little bit further. I want to actually have create a constructor. And the way that we do this is we implement for some type T, we introduce the type variable in the scope of impl. So even though we're using T up the top, if I wanted to use some other letter like A in this impl block, I could. I'm not going to. But essentially, this is why the less than and greater the delimiters there appear twice. We create a static method new, and a new takes some value of t by ownership, so by value, and it returns, and this static method returns some raw pointer of type self, which happens to be the type of the node of whatever type t is. So we could, if we wanted to, right here, send back null. Like this would actually pass the type checker. It wouldn't be especially useful because our lists would always have 0 items. So we'll start by sort of just having node. The way that new constructors, so they work by convention. There is actually no constructor in the language apart from this kind of literal syntax that we're using. We're going to pointer not null. Now the previous, actually we want next. Let's put next first because we're people and we do that. Sorry, null mute. So so you remember here our types are a mutable pointer to some node, but we have nothing there, so we need to provide null pointers to start with. Now this actually isn't enough. And the reason why it's not enough is because it's allocated on the stack. Now, and that means we're going to actually create problems for ourselves when we want to start referring backwards and forwards to things. So we're going to do something a bit weird, which is we want to put a box. So we're going to box new, but that's a box type. Like that's a valid, but a valid Rust thing. So we actually need to then take the box that we've created, which is just a smart pointer, and then we need to sort of deconstruct that into a raw pointer. Now we have our new node that contains our value on the heap with box new, and then we just kind of take its parts and get its pointers out, and now we have one pointer to a node that has 2 null pointers next to it in memory. Are you with me? I somehow think that we're not going to get through all 3 implementations in an hour. This is taking me quite a long time. I mean, I'm having fun, but I hope you are too. Goodbye ownership. Yeah, see ya. This is, by the way, this is completely not idiomatic Rust. Like, this is essentially saying to everyone who programs in Rust full time that your language is no good. Now, what's a raw pointer? A raw pointer is just a pointer that is not a smart pointer. That doesn't make any sense to you if you don't know what a smart pointer is. Another way of saying this is essentially these next and previous fields inside node are just numbers. A Rust reference also has some extra information. So for example, a reference to a slice, a reference to a string is known as a string slice, and it also has the length of the number of valid bytes that is available to it. Or this box thing is also a smart pointer. Yeah, so I'm going to leave it there. This is kind of dense topic. We'll really get derailed if I go into it in great depth. But a raw pointer just is not very smart. We need to do a lot of checking to make sure that we're not going to crash our program, which is exactly why Rust exists. And like, this is a good point that maybe actually it is okay to have raw pointers in our language. In fact, it's essential because Rust actually needs to communicate with the outside world, and this is the only vehicle that we've got. To access other places in memory, we need some way of expressing or interacting with raw pointers. Okay, now let me go back to my cheat sheet because I have lost it. I used to actually do a lot of these completely live, and I discovered very early on that I would often find myself scratching my head very frequently, and it wasn't particularly useful. So I've now got my doubly-linked list, and it contains some head, which is a mutable pointer to a node of T, and it's the tail. We have two, so we have some struct. It's actually kind of the master of, or like the supervisor, or the controller node, which actually itself isn't actually part of the list, but it always has references to the start and the end of the list. But we also have pointers between all of the nodes themselves, so it's almost like a triangle shape. All of the nodes can point to each other, and at the top we have one doubly linked list struct that points back down into the head and the tail. Now this is a problem because every single time we mutate the list, that is, we change it, we need to make sure that every single pointer is synchronized, and we need to do that in a way that that we guarantee all of the semantics that we require, like across all threads that might interact with our program. Make sure that they don't touch any of the memory that we are also interacting with. Now, Rust actually does have an advantage over C++ in this regard, and that you get that semantics, you get those kind of guarantees about not interfering with other parts of the program, sort of out of the box. That's actually not quite fair because C++ will do a good job as well. So this actually returns self. So we're creating the constructor again, and the constructor takes no arguments because it doesn't have a. We just say that we can't actually it just starts as an empty list. So there's actually no nodes to refer to. So we have another null pointer that's mutable. And that's our new method. Now we actually don't have a lot of, this isn't extremely useful very much at the moment. We could, we'll implement, so I'm just going to derive debug. I mean, if we wanted to, we could actually start by and give it a type U64, you know, it would be dangerous. We'll create our list and print it out. It's not supposed to return a bool. I don't know why it's done that. Oh, okay. It's because I got the syntax wrong. Okay, so it's there's our null pointer actually 0x0. So the null pointers are being printed out as hexadecimal, and the hexadecimal value of none is 0 is 0. So so we've got an empty list. You know, it's 10 points to us. We now want to put some actual methods onto there. Oh, sorry, some actual items. So we'll create two methods. One will be append, and the other will be remove. we need to take self by reference. So we are borrowing a self value of t, and then we're going to return nothing because we're just mutating in place. So the first thing we want is like our new node. Actually, we won't call it blank. We'll just call it spare. I hate calling things new, but let's just do so. Maybe new node. And we've got our constructor new, except we takes value. So we now actually have something which we can add to the list. Now we call upon our lovely friend unsafe. We need to do this because essentially there are no guarantee. The borrow checker just can't really have if the borrow checker can't really reason about raw pointers at all. It doesn't even try. It says, by the way, unsafe doesn't mean, you know, this is always dangerous. What it's saying is, I, the compiler, cannot guarantee this. So that's your job, programmer. And the unsafe keyword essentially pushing responsibility to the programmer. If we were being very strict, we would say something like safety. We know this is safe because ... where ... is some reason. And we chuck. It's a good reason. Now, if the tail is null, then put the, it means that we are right at this is the very first time we're inserting. So we can actually put new node at the start. And this will make sense very shortly. Otherwise, and I'll just self. So we're always appending. So we're always putting the thing at the start, right? So this is actually, this would have been a better place to start. So we always add to the end. Now, what about the beginning? So if there is nothing, if we've got an empty list, then we'll just say that new node is both the start and the end. But if it's not, we have some work to do, and we need to do a lot. So we need to take tail and actually say so we're pushing things onto the end, and that means we need to adjust the next field of the current tail and say that that's the new node. And for the new node, its previous becomes the current tail, right? Are you with me? If not, that's okay, because, you know, pointer semantics is, you know, difficult. This is why we have a borrow checker. Again, I sort of doubt my abilities to get through all my 3 implementations in the next 25 minutes, but I'm just going to try and see how many people stick around. By the way, if you can't read the, we are actually not, if you've just joined the stream, welcome. I am just 2/3 of the way through the first implementation, so there's still heaps to go. Feel free to introduce yourself and shake hands with anyone around you. Anyone else in the room. There are a couple of people commenting in the chat, which you are welcome to join too. Now, we need to remove something. And we're going to call that something a target node. And there we go. Now this is also really ugly. So I apologize if you are sweating a little bit. But we're going to also call on our good friend unsafe, because nothing about removing, nothing about this operation is going to be safe. Okay, so our job is to iterate through the list, starting at the head. We know where the head is because we are actually the supervisor node at the top, the controller, the thing that's at the top of, like, has the links to both the start and the end. But once we find it, like, life is going to change. Okay, so we'll start by dereferencing target and checking its previous. If it's not null, we already have a problem. Because what we are saying, like, look, if the node that we want to delete isn't at the like has its own links, we need to update those at the same time and all the rest of them, right? So we need to, and here we go again. So if it's not null, that means there's something extra we've got to do. So let's dereference target again and update. So this is the previous node is this thing. So we're actually accessing it twice. Wrap that in parentheses also. And update the next target's current next. So we're going to update all of the pointers before we actually delete the thing itself. The deletion is pretty easy because Rust's drop semantics will take care of that for us. So what we're doing is we're updating the previous node and giving the next. We're just deleting ourselves. We're kind of extracting ourselves, or extracting target from the list, and then updating, rewiring all the pointers together. Okay. If it is null, and now suddenly I don't like this. When I program, I tend to do things like, I don't like having inversion, like I don't like double negatives in my I don't like double negatives in my code and like in my conditionals. So maybe this is slightly easier to reason about. We'll see. It's probably the good thing. I say the good thing. The good thing is you've got excellent unit tests for this, like, don't you? I shouldn't laugh. Okay, so if now we want to update its next, I'm taking a long time to get to the point. Apologies. We do the same thing for the next pointer. If it's null, then we are at the end, right? Or and let's kind of repeat this pattern of having dereference target and checking for its next. So we've dealt with the previous pointer, so now we're dealing with the next pointer, and so we need to get do this crazy thing again. So we need the previous of the next, and then assign it to the previous of target. Does that make any sense? I don't know, maybe. That, I think, is remove. And now we've still got a target in memory with raw pointers. And if you know anything about Rust, you'll know that Rust doesn't like deleting things that are raw pointers. So we need to make sure that we don't leak memory. We actually need to delete target. But we have no delete button on target. Like target delete isn't a thing. And drop target is also slightly undefined. We could actually implement drop on target, but instead I'm just going to cheat and just do it here. By creating a box has valid drop semantics, and we can just make use of them right here. So this is kind of cheating. Do I care? Not today. Now we still don't have a very good. Oh, I need to make this mutable. We don't have a. So I'm just going to quote unquote make this slightly simple. Simple-ish. Oh God. Hi, Logan engineer. Oh, okay. Have I not got? Why is this not happy? Oh, have I got the wrong scope somehow? Oh, I. Okay, so think if. So I was trying to define a function, the remove, inside the append. And so Rust was very confused. I'm just going to reformat the code. So I can get everything right. And aha! Now, what we could, so we've got two valid pointers, and they actually point to different places. What we could do for our display method, let's say, if we implemented display, would be to iterate through all of these pointers and then bring out the whole list. I think that we'll actually pass for that right now, but this is a lovely exercise for the reader. I apologize. So some other ways to update this would be by the way, have a length method here, which would be usize, and then so this would be I think something that's useful, and then on append we would and here also this is the unsafe block. Now we've actually got a length, so we might get something that's not just a pointer. If I run it again, I should get 3. Okay, I've got length 3, and let's just see that I can delete a node. So to delete a node, I can't go and look for it and delete it. I can't delete things by value. And then, so node 2, by the way, we got a problem. Append returns, it doesn't actually return a reference to the new node that we've created. Maybe we could just do that anyway. I mean, references are cheap, right? And By the way, this completely returning reference here, like again, is another way where like completely avoiding the borrow checker. Like, do not do this. Do not have multiple multiple owners in this like across your program. This will cause problems. But not real. Like now we so the length here is 3. Oh, the reason why I wanted to do this was because I wanted to append and then list remove node 2. Now our list, in fact, what we should do to make it more interesting, instead of deleting the one that's in the middle, let's delete one of the nodes that is at the end, right? So we can print out our list at the start, and then we'll print it out afterwards. We should see the I'm going to move this over to the side, I think, so that actually that wasn't quite what I intended. I want to move panel to the right, so because I know that my face is on the top, is down the bottom left. What we should see is that the pointers as well as the length change. So, okay, go away. So this I'm going to dash clear, and then I'll run it again with dash Q for quiet. And the tail pointer did not change. That's weird. Did I actually remove it? I might, and you know why? Here is my suspicion. Because we have a local value, because we now have a local reference to the node that we actually tried to delete, Rust is like, oh, sure, that point is still valid. I think. I don't know. Anyway, so this is my raw pointer implementation. I haven't checked for comments in a long time, and I'm very curious to see if anyone has comments. So allow me to pull up the going to be deleting that in like the actual publication of the stream. Now here are the comments. Okay. Okay, so there's a lot of comments as I was going through, and head hasn't been initialized there. I think we got there. This is a really interesting question. Is there a way to just verify that what you're doing inside your unsafe block is safe? No, otherwise unsafe keyword would not exist. There are some ways to test the pointers out. And what you do is you run your code, and then under Miri. Now, Miri is an interpreter that requires nightly. Now, it's not installed. Okay. I don't have it installed on this computer. And Miri is a kind of a simulator. It will take it runs all of your tests under an interpreter and then checks that all of the references are valid. In our case, that still probably wouldn't help us because we don't have any tests. So, I'm using I'm using the cheat sheet. Boo. I'll just hide the cheat sheet and get the other one. And that is here. Ta-da! The within unsafe, the you can execute Miri. So with Rust up, install component cargo Miri, I think would be how it works, or through cargo, but that's a slightly different topic. But no, there's no way to verify that what you're doing at unsafe is completely correct. There is a really amazingly cool project called Kani, Kani, and Kani will provide the by the way, this is exactly what yeah, that's right. You did not see the cheat sheet. This was all me magically creating this on the fly. And yes, in terms of streaming, like following like one specific application rather than the screen is probably a lot definitely has the problem that you don't run into issues with revealing a whole bunch of stuff that you shouldn't. And here's another question, another point that I think is really quite useful, that there is a problem with, I think, automated testing, or at least the growth of Rust, and that is this is more broad, that there is a problem whereby people who are like senior developers don't know how to evaluate Rust. This is actually, I think, one of the reasons why it's quite hard to hire them into especially bigger companies where like the use of Rust is very uncommon, and therefore people going through interviews, the interviewers don't actually know how to assess the code. In a lot of big companies, code challenges are quite common, and these sorts of issues around unidiomatic code being pushed forward are typically because someone from some other programming language re-implemented them in Rust without actually understanding Rust. They understand the syntax, but actually not really the semantics. So anyway, this current implementation is like very bad. Please don't do this at home. By the way, I will actually give you a link to a repository. Now that you... And I haven't pushed the code up, but it will be after this. So the repository that I have just shared with you, and that is a GitHub live timClicks live streams, or live dash streams, will actually have these implementations like for you very, very soon. Look, I'm hopeful that I won't. In fact, I actually made it. I had to go through multiple coding interviews, and it was extremely odd because everyone, when I started at AWS, everyone was like, "No, I don't actually know Rust, but I really want you to do your coding." And I was like, "I can do these things in Python if you want." So, no, you should do them in Rust. And it was very strange. It was a surreal experience, being interviewed in a language that people didn't know how to interview on. Anyway. What else? Okay, so now we are going to move to reference counting, or like, let's see if we can avoid the unsafe keyword. Like, all of this is not good, but we don't need it. So let's try using something else. I'm going to introduce a couple of extra. By the way, we wanted a find. There are actually a couple of other methods that we can implement as well. So here is find. Let me walk through this. So the find method is, we have some value t that we want to check whether or not it is in the list. And here's how so to do that, we iterate through. And we start at the head. And while current is, while the node that we are checking is not null, this is a inverted logic that I probably can't really get rid of. Dereference current. So we've already, we know that this is safe. So here we go, safety. We know the pointer is non-null. If the value equals value, then return sum of current, we're done. Otherwise, get to the end of the list and we are, we haven't found it. Now, you'll notice probably that if we try and compile this code, Rust will complain. And that is because we don't have partial equality inside our, it's saying that we can't use the equality operation, the operator, this one here, can't use double equals because it's like T is not restricted to things that don't have it's not restricted to things that it can compare as equal. Now, if we do this, we can say we can implement partial equality, or we can implement linked list for everything that implements partial equality. Now we might get this to compile. So that works okay. Now we've got an interesting problem potentially later on, and that is if we try to implement doubly linked list for some T that does not implement partial equality, it's not a constraint on the list itself or a node. Now, this means that you could have a state of your program where you could essentially have it's just a kind of a slightly awkward semantics, or at least you need to, it's not in the type system of doubly linked list that T, the restriction isn't here. Oh, that's the wrong place for that. And it's arguable which one you want, because you might actually want to be able to test whether or not nodes themselves can compare against each other in all cases. Okay, and while I'm here, I want to also introduce what if we want to use this in a for loop? There was some mention before of into Iterator, which was the problem with the HackerRank implementation. So allow me to kind of give us something like that. Okay. First thing I'm going to do is give myself an iterator type. And then now I'm just going to create another method. So I'm inside the impl block. So of doubly linked list. And I'm going to create an iter method, which takes a immutable reference or a shared reference to self. And it's going to return the iterator. And of T. And so we do so, we use doubly linked iterator, list iterator, and the current node is going to be self.head. Now notice, conveniently, we don't have to worry about whether or not this is copy or clone because it's all raw pointers. So who cares? Turns out everybody cares. That's why, yeah, that's again why Rust exists. I want to get through this quickly because I'm actually severely over time. Here is the iterator. Allow me to look, sort of walk you through it. Here's my partial equality trait again. I've actually I've implemented what I'm saying here is that for every type T which supports partial equality, the equality, sorry, I can use the linked list in a for loop. Otherwise, I can't. Actually, might not even be necessary here. Wonder if it's not. Ooh. Well, the type system definitely thinks that it wants to be. Oh, there's no requirement for it to be. So I should be able to print out this call editor on it. Doesn't have all the convenient functions that are applied to. Oh yeah, okay. So very good. I need to dereference it, right? So I actually want to access the values. Arguably, the iterator should do this, but maybe we could change this. So instead of saying the item is no T, I wonder if we should actually say referenced T. Wonder if this will let me do it. View, and then you need to dereference. I need to. Sorry, everybody. Current node. I need to deref. Oh crap! What the hell happened there? Okay, so I want to. I've got current node. I want to dereference it. And then take the value, but now I need a pointer to it. So I take a. You might ask, why do you actually need a pointer to it instead of just a reference? And I think the reason is my hunch is that you need the reference to be a raw pointer because you don't really have any borrowing semantics. I could try and do it with a oh, is that not a valid thing? The arguments. Oh, what? Hello. Oh, wait. What? Ah, the wrong screen again. That was embarrassing. Luckily, it's not live. Did anyone get the joke? Okay, I'm going to try that again. A value there, and I want to take a reference to it. And then I want to cast that as a raw pointer, but so now I'm iterating over a const of U64, which is good. I mean, it's better, but still not exactly what I want. Because it would be nice to actually remove this reference, this raw pointer as well, but I don't think you can. What? Oh, okay, fine. Well, may as well just move the cast into all this. get all the yuckiness in the unsafe block. That's actually, that's a very high concentration of symbols, isn't it? I still don't actually have values. I just have pointers. That's not useful. I really do need to dereference item. Oh, no. It's unsafe. You can't. On the side. And now we should see items in the list. 1, 2. Finally. Sorry. Hurrah. We've won. Okay, well, at least I have some sort of moral victory. I have been able to beat the raw pointer. I still have a whole bunch of compiler warnings and things that I haven't even looked at properly. Unused value of box that must be used. Okay, we'll go away. I feel like this is very pedantic of you, Rust. I mean, well, congratulations. Okay, so we've got two choices really. It's we're at 1 hour. I can either keep going, which I didn't really expect to do, or but I've got a reasonable audience. We've still got, you know, a couple of. Good morning. Did you miss all the fun? Well, we're just. Hey Mara, it's nice to see you. We are just playing around with raw pointers here. It's taking me a long time to get to some of the safer stuff. But this is a this is kind of more fun, actually, saying, well, if we really want C++, we could do so. Okay, so I've got a couple of really good. So I've had a couple of people saying, no, keep going. Okay, shall I keep? I'll keep going. And yes, I'm testing in production. Can't you tell? So we had a really good question. Sorry, I'm clicking in the wrong place. And here is one. Do you have to drop the box? So what this is referring to on line 76 here, I have some box, and the reason why we are yes, this is the right thing to do. I really should add a lifetime to the iterator, but I wanted to cheat, and so I didn't. So stop being good at Rust. And we'll get back to that. Allow me to talk about the box. So the box is what is its purpose? We don't need to drop it because drop is automatically called at the end of its scope. It's slightly, the semantics are slightly different than that. But essentially, once we get to the end of this unsafe block, the box is dropped. Now, the reason why we needed to do this, so we go back to our remove method. So there'll be a bunch of people who have just joined the stream that wouldn't have seen me implement this. By the way, what a node is, let's go right back. So a node with raw pointers, we've got every node has some value of arbitrary type t. We have a next and a previous, and 2 pointers that are initialized to null. And when we construct a node, we need to do this really strange thing whereby, or at least I thought it was strange when I first sort of did it. Normally, when you create an object with the new method, you just basically use its literal form and you're fine. In our case, we need to return a mutable a mutable raw pointer to self. And so we could just sort of say, we could take a mutable mutable reference, and then cast that as a mutable pointer. That isn't very satisfactory because in the node itself, like Rust would immediately try to delete the thing after it, or at least would complain because the node would be allocated on the function stack. As soon as the function returns, the pointer would be invalid. So we actually need to place the node on the heap. And our way of doing so is to create a box. And so now node is living on the heap, and we have a local reference to it, actually a smart pointer called a box. And that's no good because we're using raw pointers. We, at least in this implementation, we we need to deconstruct the box. And then I think it's into raw. So actually, we essentially had the lovely semantics of Rust and decided to throw them away and just keep the pointers. And so all of this nonsense essentially is because we're doing everything on everything hard way. We're doing everything the hard way by saying that. And so now we can talk about remove. Remove is complicated. We start with some target node that we wish to remove from the list. And so to do so, you can imagine a chain, the physical chain. Now, just say that you wanted to remove one of the links in the chain. In this case, we actually have two chains. That's the whole point of the doubly linked list. We need to take one, and we need to take the item out of the chain, and then fuse the two link ends together. So what we do is we say, like, if my target has no previous node, then its next method becomes the head. So what this is saying is that if there are no items in the list, then the next method if we're at the previous, if we're trying to remove the head node, that's what I was trying to say, then just use the next, then just essentially pop it off the top. Otherwise, we need to find the previous node, dereference that, find its next pointer, and update the next one to the target's next. Essentially, when we try to remove one link of the chain out, we need to find this link that we're removing out from its previous and attach that to the next of, and then do that in reverse for the other side. Now, the problem that I will get to box. Now, allow me, and this is where we got to when we implemented remove. The problem we've got is we're dealing with raw pointers, and the semantics are that the Rust won't touch them. It won't delete them. So now we've potentially created a memory leak. Now, one way to avoid that is once target gets to the end of the scope, and let's say of remove, because that's where ownership of we have a reference to some node. Now we don't have any way, Rust has no way of knowing that once the remove actually means this is the appropriate time to delete target. Now there's no hey Maddie, it's awesome that you've popped in. Thank you very much for saying hi. If you have any other recommendations for things that you would like me to explain, please ask away at any time through Twitter or whatever. That's awesome. So we are we're still talking about box. Now, the so we have target here, and we need to delete it. So we know, because we are the programmers, we know that this is the appropriate time to delete target. Now, target doesn't have a delete method like it, and we arguably could call drop, which we'll use in full. Mum, drop. could call drop on target, but the target, but the drop trait actually isn't defined for a mutable pointer. Oh, sorry, a mutable raw pointer of node. So that doesn't help, and we can't implement foreign functions. We can't implement foreign traits for foreign things, foreign types, and we don't define either the drop trait from the standard library or the semantics of raw pointers. So we really can't really lean on that. So instead, we can create a box from raw parts, what this is saying, from a raw pointer, which is what we have. And so now Rust can say, aha, I have ownership over target. So what this is doing is saying there is some memory that I now control, but this box doesn't live for very long. I immediately, essentially, I'm using this underscore here to denote that I don't care about it. The compiler, if I just leave this expression as it is, the compiler will hit me up with a warning that says, oh, you have an unused value here that must be used. And let's try and run it. I'll cargo run. And that makes a lot of sense because, in fact, it's actually complaining about the return value, which is unit. But, this is an interesting thing. You should call drop. So, it actually thinks that we should call, maybe that is actually a clearer way to express our intent. Maybe that's arguably better, to explicitly call drop there. So, but we can achieve the same thing by just assigning it to something which is immediately freed, and drop is immediately called anyway. That was a very long way to explain why there is a why we're here. Oh, hopefully people have enjoyed the diversion, or let's go on to something a little bit more Rust-like. So we've dealt with raw pointers. We've told, we've been in C++ or C land for a long time. Let's and I do actually like Mara's point of we should actually have a lifetime annotation here. The reason why we don't is because essentially I want to make the point that this whole thing is cursed. The whole thing is awful. And I don't want to bind, the point around lifetimes that Mara has made, which is a really good one, is that, and I'll try and find the comment, add a lifetime to the iterator, is that we want to bind the lifetime of things that we have references to so that Rust knows how to reason about them. So it would make no sense. We want to prevent in that case, our current node from being deleted or freed by some idiot who decides to drop the box. And while I'm iterating over the thing. Now, currently, Rust will not protect us against that because we haven't actually provided we haven't actually declared the semantics that we intend in the lifetime system that we've got. So, but because we're not using Rust references, I kind of really want to move on. So this is a really nice thing to do, but we will pass for now. Okay. Okay, what do I want to do now? I think I would like to ask anyone for questions. Has anyone got any other things that they would like to me to clarify? And just while I'm getting set up for the next example, I we'll just kind of shout out that I really appreciate that people have joined the stream. I think it's really awesome. I'm going to try to come online probably every 2 weeks at about this time. I'm hoping to do one session for sort of a European audience at about, I know that Friday 10, early morning on Friday isn't ideal. And an Asian audience as well, and one for the Americas. But hopefully it's not too distracting from work. So now I want to introduce a couple of other concepts. And so the original problem that we faced, in fact, I'll bring the code back. Let's see if I can bring the code back. The original problem that we faced was that we had this conceptual understanding of what a linked list was. Now, sort of conceptual model was that this is right at the start of the stream. So if you've just joined us, that's absolutely fine. We've got a list of t, a value, and we've got some, and this is probably going to be option box. We've got our list, and this is actually going to be an item in the list, but whatever. We've got references in both directions. So this will be, now if we, this doesn't work, this will never work. It's sort of like, this will only work in a tree. Now, the problem we face is that ownership becomes extremely ambiguous here, and Rust will have none of it. Rust will not be happy with us at all. We can't have pointers heading in 2 directions. It just doesn't make sense from Rust's point of view. So one of the ways through this was what we just implemented with raw pointers, essentially telling the compiler to sit down while the programmer knows the semantics that the programmer wants, and she will happily implement them. So, and that's what I attempted to do, and in a couple of places I failed. So, and even when the choice examples like that. So now I'm going to introduce a couple of extra pieces of tooling that I have from the standard library. One of them is called RefCell, and the other one is, in fact, there's 2, I suppose. We've got 2 types of smart pointers. One is a reference counter, and one is a weak reference counter. This RefCell thing provides what we call interior mutability in the business. One may ask, quite rightfully, what on earth is interior mutability? And I would be interested to see any responses in the comments about the like, how do you define interior mutability? Because it's quite an interesting question. I have these awful type definitions, which I am going to share, like I'm going to walk through, but I'm just going to check the comments to see if anyone has had an attempt at trying to implement, or just trying to find an interior mutability. So far, I haven't seen any, which is fine, you know. So I'll have a go. The interior mutability provides this kind of slightly mind-bending utility, which is the ability to modify a value which has been declared as immutable. There are a couple of things that are so this is essentially, it sounds like it's breaking the rules, but it turns out that it actually works okay. because the rules around immutable, we call this like an immutable reference. So the immutable reference is also known as a unique, is a shared pointer. And we've got some ampersand t. So this is known as a so-called immutable reference or shared reference. Now, it turns out that Rust actually doesn't care about immutability. What Rust cares about is the sharing and what's known as aliasing. And in particular, what Rust guarantees is that the references are actually pointing in the right place, and that if you have two different mutable pointers, that there is only one of those, and at any given time, and that they don't alias. So two different pointers to two different things, two different variables don't actually refer accidentally to the same thing in memory. Now, RefCell enables us to kind of get around this main function. Okay, go away. Hopefully I haven't angered anybody by describing things in those terms. It'll be interesting to see whether or not people, want to burn me. And I'm just for fun, or I suppose for convenience, I'm going to implement derive debug. And now I've got my node available. We can do a couple of fun things. So we can implement, so we just add type variable into scope, and then I've got node of t, and I want to implement a constructor. So this is by convention called new, and it takes, in our case, we actually will require some object t, or some item of t to start, because it doesn't make any sense to have an item with nothing inside it. At least not for this data structure. Now, our return type is complicated. I have a RC, which is a reference counted pointer, or reference count to, and it has ownership over some RefCell, which is a thing that provides interior immutability of self. So we've got a node, which, by the way, also sort of wraps t, or contains some item t, and the type signatures do get a bit disgusting. I apologize for that, but essentially we've got this one here. So node, by the way, will always, we could return some here just so that it's, no, we won't. Okay, so now how do we start? We start, so value is relatively simple, and then previous is none, and next is none also. This isn't quite enough. We need to actually wrap our smart pointers and stuff and do that. So we want RefCell new. And then we're going to say, actually create a reference counter as well and make that new too. Cool. Oh, okay, so we've got items. Now what we really want is an actual list. See that my typing is really going bad. It's like 10:30 at night. Love coding at 10:30 at night. It's great. Struct. You know, when I was a lot younger, I used to really enjoy like all-night coding sessions, but not as good as it used to be. So this is actually going to look very similar to our last linked list. This is going to be our it looks kind of exactly the same. The internals are much, much different. We've got a weak, sorry, just a link, a strong link to T, and the end of the list is going to be a weak link. By the way, we really need to make sure that we've got the weak links and the strong links in the right place. Otherwise, life will become very painful very quickly. And just to start off, I'm going to create an implement method with some type variable t. And if you're relatively new to Rust, every impl block can kind of redefine its own type variable. So I could do anything I wanted inside the context of T, so inside the context of the block itself, and that the code would actually be happy. But annoyingly, you can't just use T across the whole function. I've always kind of hated that. There are reasons that I understand about the fact that impl blocks are sort of isolated, and you can add impl blocks. One of the cool things about Rust is that you are able to implement or like extend other types. Like I can actually create a trait in my own function and then implement that trait for some standard library type. And essentially it feels a lot like monkey patching. Use Ruby or Python, but it's much, much more type safe. Creating our Doubly-Linked list is really simple to start with. I just say that I've got nothing. I start with an empty list. And we'll say that, you know, this time we will be like extra cool, I say. I have a Doubly-Linked list of char, and we'll call new there. This will be empty to start with. Because we haven't got any items yet. So all we should see is Doubly-Linked list none at this stage. And so the line we care about is highlighted down the bottom here. Everything else is kind of annoying because we get unused warnings, which we could eliminate, but we're soon going to actually use them. So I'm just going to check in for comments, and oh look, we've got interior mutability means one can change the interior drapes and the color schemes. I like it. The one way to say, let's see if I can. I've heard it expressed that a interior mutability is like having like two physical boxes, and the type itself has a key to the inner box, like the inner lock. It's not actually a lock in terms of like computer science lock, but everyone else, when they take a reference to it, to your thing, they only get access to the outside layer. Okay, so I am going to, what am I going to do? I'm going to create an append method. So we actually want to add items to the list. And so I'm going to create a public function, append. And to do, I'm going to take a mutable reference or a unique reference to self, and then I want some value of type T, and I am not going, I'm not going to return a reference to T. I think that we might need it later on. Maybe we won't. We'll see. Node value. Okay, so we immediately create the node. Now, the node doesn't have its next and previous fields are initialized to none, which is an extreme. And so now we're essentially going to wire them into the current list. Okay, so there are a few ways we could do this. We need to, sorry, I'm saying to you, is this unhappy? Arm is not covered. Yes, I know that arm is. Okay, so we're currently looking at the tail, and what we get back is a weak reference. Potentially, we might get none, but at this stage we're dealing with a weak reference, and so I want to show you something. I actually want to take clone, or let's do it this way. So what is new node? It's an RC of ref. So I actually want to clone or increment the reference count. I can do that by calling clone on. Why are you unhappy? Expected a reference of RC but found RC. Okay. If this will work. Oh, it's just type problems. Maybe this will be happier. It's just unhappy because the type system is. Oh, it's just the Rust analyzer is a bit confused because I'm not actually doing what I would like to do. So, for simplicity, I'm going to actually increment the reference count and then wrap it in an option. And then I want to update the old tails reference to point to the new node. Now, to do so, I need to go through quite a lot of bureaucracy. I need to upgrade the weak pointer to an actual pointer. Sorry, like and then I'm just going to unwrap. So we get the type system. So we had weak, and now we have an actual reference count. And why is this unhappy? Again, because of and now I need to strong borrow mute and then update its next field. So what we're doing is we're taking we have a reference to the old tail, and we're trying to get a mutable borrow of that node, and then changing its next pointer to the new node, essentially. Now, okay, yep. Now, why am I surprised that that worked? I don't know. By convention, I just want to see if this will work now and be a little bit happier. We just to like confirm our intent, we use the static method of the RC type clone rather than the clone method of the reference counter itself, because it's sometimes ambiguous when you're reading what you actually intended. Did you intend to duplicate the item that the reference counter is referring to, or just the reference count itself? Okay, so now we need to kind of deal with the none case properly. None case is pretty easy. We self head it's just our reference. I wonder if I can actually just, no, I do. Well, I was just going to say, can I create this variable somewhere and just use that? But okay, so down the bottom, I'm not quite done because I've got a strong thing. Oh, here I need new node. I've got a strong reference to it, but I still want to append to the tail. So append, by the way, just if we remember, append is just adding it to the end. But at the end of the link, I need to have my reference counter and then downgrade to a weak link. And that's new node. It's not quite what I need. I need an option, and then self.tail. So now the end of the list points to, and so this tail here is a weak link, which is good. Now the head points to, oh, sorry, in the none case, head points there too, which is good, and it's a strong reference. And if we had some old tail, we've updated its next field to point to me, the new node, as a strong pointer, as a strong reference count. Okay, so that's confusing, but that works. So now we should be able to append some values. We're being extremely exciting with our alphabet. This should actually work. Aha. And by the way, one thing that's kind of interesting, unlike raw pointers, we have more information from the type system. So Rust can actually, in its debug implementation of all of these types, actually provides a something that's a little bit close to more reasonable than just a pointer. We actually can dig in and find the values straight from dref. Now that's still kind of ugly. So if I add the hash mark and run it again, I might get again, it's not nice, but if you squint, it is what we asked for. We've got a doubly linked list, and the head is a reference to here, to sum. And the weak doesn't have the same semantics. So we start at the head, we get our first item, so it's a reference cell of A, and then the next item is B, and then C. And notice, by the way, that that's interesting. The previous item, isn't what we want. Why do they not point back to, oh, have we not added that? By the way, so this is just while we get to that, just a side question, why create type aliases for link and weak link, but not for RefCell? Yeah, that's a good question. I wasn't quite sure if we wanted another type alias. And I don't even know what you call it. That basically meant that like this, we don't have to use the RefCell as frequently. Like we could call it like a strong node and a weak node potentially. Yeah, essentially just stylistic. I wonder if I should complete the I should complete the append though. So what we need to, so at the moment we only have nexts, but we haven't updated any previous fields. So how do we do that? So I need to create weak links. We've got one at tail. But we need for all of these other ones to do that as well. So if I'm at the tail, there is no previous. So where would how would I do it? Sorry, my brain is a bit dead at the moment. I wonder if so I've got tail, it should have, I wonder if, oh gosh. That's the thing. Okay. Okay, so if I have, so this strong thing is a reference to the old tail. Now it's previous. So when I'm inserting something, the old one is the new oh gosh, why can't I figure this out? My brain is just, this is super basic. I just need to insert previous somewhere. Okay, sorry. I just read this comment around, is it night owl? Yeah, for me, it's just, it's close to 11 o'clock now. And I want to fix this. So I wonder if I can look at the head and go the other way around. No, surely not. I'm gonna have to think about this again. But actually, you know what I should do? I'm not making any forward progress. I am going to pause there and congratulate you for turning up at 3:30 in the morning or 3:45. I can't believe you found this. And I'm just going to hang up because this didn't quite end out. This is where I wanted it to get to. I had a lot of fun though. So hopefully this was enjoyable for you, and feel free to catch me online and we can talk about other ways to get this working, I think. And I do actually have one more implementation for you, but I am not going to get there because I just don't have the time and I've really got to go to bed. I'm exhausted. Thank you all again, and have a really lovely day or evening or morning, and I will see you again. Sorry I couldn't get this. I'm looking at it again off the screen and I still just it's a one-line change, and I just can't figure it out, and it's really bugging me. And I don't want to. Oh, I just really want to fix it, and I just can't, and I don't even know how to start, and my brain won't work. So I am going to hang out. It's been really fun to chat, and if you have any other ideas for future streams, just please ask, and I'll see if we can get around to them. Okay, cheers, bye.